È tempo di cominciare, ci siamo tutti, è attivato anche lo streaming e quindi è con grande piacere che vi presento il professor Rodolfo Bonifacio, recentemente nominato anche emerito all'Università di Milano, e riassumere tutta la sua attività in poche parole è un po' difficile, mi focalizzerò su pochi punti essenziali. E Rodolfo Bonifacio, insieme a Pellegrini Narducci, è famosissimo per il lavoro che ha pubblicato nell'84, dove per la prima volta si spiegava l'effetto di emissione spontanea amplificata in un laser a elettroni liberi, e questo ha aperto la strada a tutte le generazioni future e presenti di FEL ai raggi X, cominciare dal CLS, da SACLA in Giappone, lo Swiss FEL in Svizzera. Ed è stato grazie a quel lavoro, che è uno tra i più citati nell'ambito della fisica degli acceleratori, che si è potuto capire che si poteva fare un laser a raggi X senza l'uso di specchi e quindi superare le difficoltà.
Single pass.
E ben sapete poi che un laser a elettroni liberi ha tanti vantaggi, tra i quali quello di essere tunabile, cambiando semplicemente l'energia degli elettroni, ed essere uno strumento che aprirà un futuro alla scienza non soltanto fisica ma anche biologica, chimica, eccetera. Però ovviamente il suo contributo non si è fermato qui, ha continuato poi con l'analisi della generazione di armoniche, con l'analisi dello spettro prodotto da un laser a elettroni liberi, dimostrando anche che esiste un regime cosiddetto di singola spike, che attualmente è utilizzato con grande piacere dagli utenti, che produce uno spettro particolarmente stretto anche in questo sistema tendenzialmente caotico. In passato Rodolfo aveva già fatto delle cose estremamente importanti, forse voi vi ricordate le equazioni di Maxwell-Bloch che descrivono la interazione tra la luce e la materia. Ecco, queste in realtà sono state derivate da Arecchi e Bonifacio nel suo lavoro di tesi nel 65, sono chiamate Maxwell-Bloch ma più propriamente dovrebbero essere chiamate Arecchi-Bonifacio, e anche Nature ha recentemente riconosciuto questa paternità con una comunicazione che è stata pubblicata un paio d'anni fa. Adesso si sta occupando di un modello totalmente quantistico del laser a elettroni liberi, una novità assoluta, e anche questo potrebbe aprire nuove prospettive che il modello classico non dimostra. E oltretutto lo ha fatto generalizzando un lavoro che sta facendo anche sugli atomi freddi e i Bose-Einstein condensate, dimostrando che ci sono dei regimi inesplorati e particolarmente utili. Va bene, io non vorrei tediarvi oltre, vi ringrazio di essere presenti e lascio a Rodolfo la parola.
Parla tu.
Non mi sono preparato.
Grazie Massimo.
Vabbè,
Massimo sa meglio di me quello che ho fatto io, molto meglio, e lo sa dire molto meglio. Dunque, però, oltre a occuparmi del FEL, Free Electron Laser, io per anni ho avuto un amore nascosto. L'ultimo lavoro, infatti, pubblicato, non molti, sulla questione del tempo, che è la mia, è stato con il collega Tombesi nel 2001, poi 16 anni fa, poi silenzio, vi dirò perché, insomma, è un problema un po' pericoloso. Io in questo seminario, ecco, facciamo così, seguiamo le trasparenze. Il mio seminario ha un titolo che è un punto interrogativo. Che cos'è il tempo? Poi infatti non vi dirò cos'è il tempo. Parlerò un po' del problema del tempo, secondo me vi dirò perché la descrizione dell'evoluzione temporale in tutte le equazioni fondamentali della fisica non funziona bene, deve essere rivista, e proporrò una nostra soluzione, hanno partecipato altri colleghi, al problema di cui vi parlerò, che riguarda il punto cos'è il tempo. Però questa domanda non è nuova, è un po' datata. Agostino da Ippona, 345-430 d.C., I know what is time. Oh, sorry, I have to speak in English. Okay, sorry. I know what is time, but if somebody asks me, I don't know what to say. Io direi che ancora adesso non è molto chiaro cosa dire. Allora, io dirò, prima, is there any problem? No, ok. If you have any question, you just raise your hand and I stop, ok? What? No, lui non parla italiano, è sufficiente. No, no, absolutely. For me it's not a problem to speak in English. I just forget sometimes, but English, okay? Now, time in physics at the moment, okay? In relativity, time in physics, okay, here. In relativity, time is the fourth component of the position tetravector, x, y, z, ct. However, in quantum mechanics, the first three components become the so-called observable operator, x, y, z, which do not commute with the other four tetravector, which is the momentum tetravector. They are the three components of the momentum tetravector. They are non-commuting operators, observable, which means that they are Hermitian and blah, blah. But then you ask to Tombesi, what does it mean exactly, observable? Professor Tombesi. But the first three components become quantized, but the time remains a parameter. A continuous parameter. All attempts to quantize time has failed miserably, leading to contradiction. No, didn't work. And I will not do it. I'm not going to quantize time. Relax. No. Now, let me say something. This famous uncertainty relation between x and px and ypy and blah, blah, in quantum mechanics formally, it's become a theorem. It's a theorem. You derive it from the formula of quantum mechanics, which is called the lemma Jordan. This is true? Paolo? Yes. Lemma Jordan lemma. But the famous energy-time uncertainty relation remains a principle, no? Like at the beginning for x and px, okay, of the order of h, blah, 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 blah. Does not derive as a theorem. It's a principle. In particular, whether you can define clearly what is delta E, and then we write it there, but the meaning, the meaning is of delta T is very imprecise. It's very vague. So it remains a principle, unlike this for x and px. Last point, all the fundamental equations of physics, in all the time is irreversible. There is no time error. That is, time can go like this and like this, or I can get younger. Unfortunately, it's not true. Okay? In reality, there is always a time error. To what is due? Let's discuss it. Okay? But time, there is no error in the fundamental equation of physics. Change time minus time, it is okay, perfectly okay. What is wrong, in my opinion? Then I don't know what it is, but let me, hey, come on. What is wrong? In all fundamental equations of physics, the time evolution is given at each instant. You give the state of the system at each instant. You derive, you give the initial condition for the wave function of what it is at an instant. What is an instant? A zero interval of time. I claim that nothing happened in an instant. Nothing. In particular, in quantum mechanics, the specification of the initial state requires a measurement of a complete set of observables to specify the wave function of what is the state of the system. But you cannot measure anything. I insist, anything in an instant, in a zero time interval. In my opinion, the instant is a mathematical artifact of the differential calculus, Newton, with no physical correspondence. Thank you for saying yes. I like that. So, in my opinion, the instant concept must be removed from physics because there's no physical meaning, there's no counterpart in the reality. Short review for people who are not experts. Huh? I remember to you that the most basic equation of non-relativistic physics is the so-called Liouville-von Neumann equation for the density operator, rho, which describes the state of the system. The rho over dt equals the commutator between h and rho. This is, if you, instead of the commutator, you write the Poisson, the Gibbs, come si chiama? Poisson parenthesis, you have the Gibbs equation for the density in Liouville space. The famous correspondence in which Liouville parenthesis goes into the commutator, and then you have the quantum version. This is the quantum version. Each is the system Hamiltonian. Now, if rho is a pure state, which means a projector on a wave function of psi, then equation, no, first of all, sorry, trace of rho square is also 1. Not only trace of rho is 1, but trace of rho square is 1. So, and this equation, this equation, is equivalent to the Schrödinger equation, but only if rho is a pure state. But for a statistical mixture, system in thermal equilibrium, for example, are not in a pure state, are in statistical mixture. A superposition of projector, not one projector, a superposition, then the Schrödinger equation is meaningless. Okay? And you must use the rho operator and the Liouville-von Neumann equation. So this is a generalization. The Liouville-von Neumann equation is a generalization of this equation to describe statistical mixture. Now, equation 1, as well as equation 2, give a unitary time evolution. With a unitary time evolution, there is no time error. Time can go one direction or the other direction with no problems. Now, what I propose, I don't propose to quantize time. But you know, there is a derivative of rho to respect to t, a derivative. I propose to substitute the derivative with an incremental ratio. Here, a retarded incremental ratio. For technical reasons, otherwise there is divergence. By the way, that's the proposal. I made a long time ago, first of all with Caldirola, my professor Caldirola, in 82, and then I discussed it in a different way, this equation with Olivares, Tombesi, and Vitali. Tombesi is here in a physical review. Right? I anticipate the reference 1 has been ignored, whereas a reference 2, in a sense, has been considered heretical by the establishment of physics. How do you dare to modify that? But even if this in the paper with Tombesi et al., we are not so explicit as in the statement I'm making now. Now, what is the property of equation 2? I will not bother you with mathematics. You just accept it. Okay? Just mathematics. The property of equation 2 is that you have a non-unitary time evolution. Non-unitary. The time evolution is not, yes, the semi-group property, but is non-unitary. So, a time arrow can appear. Because unitary means t minus t. Non-unitary, you can do that. Now, in equation 1, the Liouville equation, not only, trace rho is preserved. Why? You take the trace of this at both sides, and I remember to you that the trace of the commutator is 0. So trace of rho t minus trace of is equal to 0, and so the trace of rho is preserved. But also trace of rho square, because if trace of rho square equal 1 and preserved, you have a pure state. It's a theorem, very famous. But trace rho square is not preserved by this equation, by the finite-difference equation. It's preserved by the Liouville von Neumann equation, but not from this one. Just changing tau in minus tau, just substituting the derivative with an incremental ratio. So the state can evolve to a statistical mixture, even if you have initially a pure state. Now, this is a very important problem. Mathematically, this equation gives a multivalued function solution as multivalued complex problem, complex algebra problem. But there is a unique meaning of this equation if you specify the system only a time multiple, integer multiple of tau, whatever is tau. Okay? And then there is a unique solution, very defined, okay? If t over tau is an integer, with k equal 1, 2, 3. So, this equation does not specify the density, the state of the system at each instant, but only by interval tau, in interval tau, without quantizing the time. So the instantaneous description goes away. You don't have any more to specify the system at the instant 0, but in the first interval tau, and then you have the solution, as I show you in the next. Little mathematics. So the references are here. The last one is 2000 with Tomesi and with others. And now, let me bother you with the last mathematics. It is good to go to the energy representation. It is used to use the eigenstate of the Hamiltonian corresponding to eigenvalues En. Okay? So, the previous equation, finite difference, become this simple equation for the matrix element. And believe me, instead of the commutator here, you have minus I, omega n, m. What is omega n, m? Are the Born transition frequency. Very physical. En minus em, trivial to do that, okay? Trivial, accept it, okay? Divided h bar. Now, we can write without super operator and so on, but for the solution of this equation is absolutely trivial. It's written below. Here. You take tau on the other side, and you isolate rho and m. And you have these solutions written here. But I use the continuous solution. But strictly, for t equal k tau, rho blah blah, at time k, in the interval k is given by the rho and m in the instant, in the interval, in the first interval, k equal 1, by time this expression. But now, let's maintain the continuous solution, and then the mathematics is almost done. In the limit, this is trivial. Tau going to 0, from this becomes the derivative. Derivative is the definition of derivative. And the solution is, you look at the definition of the number A, become e to the minus I omega n. These are the usual oscillating solution for the off-diagonal elements, because omega n m is equal to 0 if n equal m. But, in my opinion, the limit tau going to 0 cannot be taken, as you see in the next transparency, but we get back to physics. And please look that rho and n, the diagonal elements, with this equation, if you take n equal n, then the transition frequency are 0, and so rho nn t is a constant. That is, what does it mean? Rho nn is the probability of occupation of the eigenstate of the energy n. So if they are constant, it means simply that the Hamiltonian is a constant. The energy is a constant. There is no dissipation. If the energy is constant, this is not whatever I have described here is a non-dissipative process. Okay? But let's go. But something happened. This solution I've written to you in the exponential form here can be written under exercise of complex number. This can be written as this. Now look at that. A to the minus gamma, blah, 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 gamma real, e to the minus oscillating time gamma. And gamma and m are written here. And the frequency nu and m are written here. Now, what you get for tau going to 0? That gamma and m goes to 0. That is, there is no damping here, tau going to 0, and the frequency becomes the Bose transition frequency. But for tau different than 0 and n different than m, otherwise this goes to 0, then the off-diagonal elements are damped. I mean that even if rho and m, whatever is the initial form, even if they are off-diagonal elements, go to the diagonal form, because all the off-diagonal are suppressed. And this is irreversible. The diagonal form is an equilibrium form. It commutes with the Hamiltonian. It's an equilibrium form. It's called a microcanonical equilibrium. Okay? So here, introducing the finite difference with a finite tau, you have a time error without quantizing time and nothing, and without dissipation. Please, this has nothing to do with the usual master equation approach who use the interaction with the universe or I don't know what. No, this is intrinsic of the finite difference equation, if tau is finite. But tau, I think, is finite. My proposal for tau, written for the first time with Caldirola, is this. The tau is equal to h bar over 2 delta E, where delta E is constant, is the mean square deviation quantum mechanically calculated depending on of h. And this is a constant of motion, so this delta E and then tau depends only on the initial state of the system and on h, which is the dynamical structure of the system. If this is, excuse me, note, tau, oh Jesus. Tau times delta E is h bar over 2. Delta T, delta E of the order of h. Tau delta E is h bar over 2. So it's the minimum possible interval of time in agreement with the time energy system. But now I give a precise meaning to the time energy energy relation, because tau is the characteristic time, is the cronon of the system. It appears in the evolution equation as a unique meaning. Now, if this is true, if I state this, the limit tau going to 0 cannot be taken, because tau going to 0 will imply an infinite spread in the energy. Then, if this is true, we have a precise statement of time-energy uncertainty relation with no time quantization. Tau is not a universal time, Planck time, no. Is a characteristic time of the system. It depends only on the Hamiltonian and on the initial state, because that's a constant. Any question? Question. Did tau already appears in the literature. Is there any experimental evidence for my statements? Yes. And now let's go. First, probably not everybody knows about the Caldirola cronon because it's old stuff, 1978 and 1994, the last one. But then, let me summarize. That's considered a free electron in minimum uncertainty wave packet, minimum. Then tau h bar can be written, very easily shown, that this can be as the spread in position, I assume movement in the x direction, on the x-axis, divided by v, where v is the average of p divided by m. It's the velocity. So this is an obvious expression. V times tau is the energy, is the position spread. So this becomes an obvious expression. Now, from the finite-difference equation, just with little mathematics, one can see that V of t, blah, 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 m, if f external, free electron, 0. 0. Now, if I expand V of t minus tau up to the second order in tau, blah, blah, very trivially, I get this equation. VW dot, sorry, I'm really sorry. VW dot. Now, the solution of this equation are V equals 0 and V equal V0. But this is increasing exponentially. The electron can be or at rest, this is VW dot, I'm really sorry, I apologize. Or is accelerating. This with VW dot is the Abram-Lorentz equation of motion with self-accelerating electron that you find in the Jackson book. Page 381. Now, let's assume that the electron is not localized, but the spread in its position is the classical electron radius. This is what Caldirola assumed. What you have to get together. Let's assume that V is, but this is non-relativistic. The relativistic extension is very simple. It's the same. V of the order of C, then delta x over V becomes the electron radius divided by C. And this is the Caldirola cronon, introduced this time as in the finite-difference equation for the electron in its own field, for the free electron. But only if you expand to second order this quantity here, and you stop to second order, you have the Abram-Lorentz equation with self-accelerating solution, absurd. But if you don't do that, then if you have f equals 0, this is that V of t equal V of t minus tau. This is V is constant. So the self-accelerating solution is an artifact of the expansion to the second order in V of t minus tau. The exact solution is trivial. So iterating V equal constant. Question? No. Now, but there is nothing more yes, there is something, there is an evidence, and there is an evidence, experimental evidence. There are many, but I quote for me what is the most important. I don't quote all the others. There are many others. In this paper, oh Jesus, in this paper, there are these that I will tell you and other experiments which can be fitted by this theory, in which tau, in the paper with Tombesi, tau is not h bar over delta E, but is an uncertainty in the interaction time. But I can derive the same uncertainty I've shown to David and Stefano with my expression. By the way, what is cavity QED? Okay, the 90% of Nobel Prize to a Roche, reference one is Michel Brun, et al. Is also Sergio Ross, the Nobel Prize. Now, cavity quantum electrodynamics experiment. In particular, the observation of vacuum-induced Rabi oscillation between excited state and ground state in rubidium atoms prepared in the... You take rubidium, you strike the electron in rubidium atom one at a time at the excited state of Rydberg state. Why Rydberg state? They decay in milliseconds. They decay in infinite time, and they have an enormous dipole moment, very good. So it's a two-level system. Excited to the ground is a two-level system. And there is a very well-known theory by Jensen chemists how to predict the behavior of a two-level system. Okay? These atoms are injected in a high Q, what is a superconducting cavity, is it true? With a reflectivity enormous. So they emit the atoms, they reabsorb the atom and go up. And they emit and go down, up and down. The so-called Rabi oscillation, a two-level system. So the expected solution is this one. Is a psi square to be the probability to go to the ground state is this, sine square. I apologize, Rodolfo, but you think you don't know trigonometry. We don't know. And you write this triviality. I tell you why. Because the observed result is not this, but is fitted by this if you put in front of the cosine e to the minus gamma t. A damping. The oscillations are damped. And this is the experimental result. I show to you. Sorry. That's the paper. Quantum direct test of field quantization. Yes, field quantization, because you have a cavity in a very 3 Kelvin, so the field is in a vacuum state. So the oscillation induced by the vacuum state field or purely quantum mechanical. And this is these dots are, this is taken from this reference. These dots are the experimental points, and this is the dark line is the observed. Damped to 0.5. As you can see, you predict from this fitting formula I've shown you before. Here, a to the minus. If you put this, the oscillation will be damped to, this goes to 0, you have as the P ground goes to 0.5. And experimentally, 1 over gamma, the time in which you go is 40 microseconds. But this is cavity losses. No, the cavity losses are 220 microseconds. So cavity losses cannot be invoked. Experimentalists and they are rushing, we have many discussions. They say dark counts, technicality, or collision with background gas, but this would give an overall reduction of the Rabi oscillation, not an approach to 0.5. Up to now, I do not have seen other fitting of this experimental result, except the one given in the paper of 2001 with this colleague, this paper here. No, I didn't see a qualitative and quantitative derivation of this result, as we get from our theory. I say, given an unrealistic explanation, because it's the one I told you now, one second ago. Our theory leads to the fitting formula, this one, with 1 over gamma in agreement with the observed value, 40 microseconds. But this paper has been considered heretic by the establishment of physics. No, not by the establishment, a colleague, David Vitali informed me, Olivares, that there are many, now there are a lot of, many people that are quoting this paper. But the time in particular, Sergio Roche, before this paper was a very good friend of mine. After this paper, he didn't look anymore to my face. Okay, go on. Let's go. Conclusion. As I said, in the paper with Tombesi, Vitali, etc., in the physical review, there are other experiments with trapped ions, vero Paolo? But I must restrict to the essential. Okay? Now, in conclusion. Oh, Jesus. Anomalies, I have described anomalies in described time as a continuous parameter. I have criticized the instant concept in physics. I have introduced the finite-difference equation giving a time evolution for finite step, tau, and leading to a time error, decoherence, that is destruction of the off-diagonal elements of the density operator. This gives a precise statement of the time energy uncertainty relation with no time quantization. This tau is the heart of the proposed modification of the evolution equation. It's precise statement. It's not imprecise, the definition of the uncertainty relation. The Caldirola cronon is obtained. It is a particular case cancelling, the Abra-Lorentz self-accelerating solution for free electron. The interpretation of experimental results that I've shown to you by Roche and et al. In cavity QED. Now, if some young researchers didn't like my talk, please forget about it, or you run a risk to be considered an heretic. As I abandoned it also in 2000 after the paper with him and seeing this horrible reaction in some conference, blah, blah, I abandoned the problem up to now. But now I come back because I'm 76 and I don't care, okay? And I will write that in a paper. I don't care, okay? They can, but I'm not afraid. At that time, I wanted to have some more career, so I dedicated myself completely to the free electron days. Now, acknowledgement, I'm grateful to Hirschan Fares, he's there, for writing with some mistake the equation. If anything is wrong, it is his fault, okay? Thank you.
Thank you very much, Rodolfo, for this very heretic talk. Tonight you
it was
deserve a
amusing.
dinner in Campo dei Fiori. We will go together.
To Campo dei Fiori, you burn me. Ah!